Okay, good evening again for the another week of this Introduction to Semiconductor Fundamentals course, where we have to revise some of the concepts as well as solve some of the problems related to the concepts which we have discussed in the lecture taught by Professor Naresh Imani. And I am Shazan Bhatt from IIT Bombay and working in Applied Quantum Mechanics Lab and the Electrical Engineering Department. And today's topic is going to be PN junction diode, and we will transition into the PN junction and see uh, how we can now make a realistic device from whatever we have been studying till now, starting from solving the basic quantum mechanical problem of potential wells, how that implements itself and how that manifests itself in the electronic devices and the day-to-day devices we use in our daily life. Let's say your mobile processors, your mobile phones, your laptops, all of the electronic equipments. The fundamental thing is going to be always this PN diode in terms of different configurations, obviously. So that's what we are going to see, that how we are going to jump from the basics we have covered already, starting from chronic penny, then moving into the blocks theorem, and how we are going to transition into the into PN diode. Okay, so what we earlier discussed is something you might be knowing about what we discussed. We started from the basic atom, and then we showed how we can write its potential, how we can discretize its energy. Then we moved into the solids where there are different atoms, and we solved something like these potential wells, where we showed that it gives rise to something like these types of potentials, and due to this there is something called as Bloch's theorem we use. Bloch's theorem which basically uses the concept of periodicity. And with the help of this, we know that if you know the wave function in any of the unit cell, let's say something which is repeating, and if you know the wave function here, then you can know the wave function of electron at the other location. Just a phase vector will be added. So it is something like this. And then we use the chronic penny model in order to in order to go into the something called as band diagram, where we actually get something on we get an implicit equation as the solution of it. When we solve the Schrodinger equation using these types of potential wells, we get an implicit equation where these two equations, where the left hand side and the right hand side are plotted onto a same plot, where they are plotted onto a same graph rather, where the right hand side is somewhere like something like cos k that limits the value between +1 and -1, and the right hand side is something like a sine hyperbolic, and you get something like this. And there you say that all of these values are allowed energy levels, and if something is in between, let's say these are not allowed energy values, and you transition into something called as extended zone representation of the band diagram, where you get bands like these. So you get something like these on both of the sides, and this is the zone representation extended zone representation, and this is E. Okay, so now extended zone representation clearly shows these different not allowed states for the electrons. Okay, so then we jumped or understood that we have to understand it in terms of what is happening in a single something called as Brillouin zone, if you understand what's happening to an electron in a single Brillouin zone, you can understand it of what is happening to an electron in an entire crystal because it's a repetitive crystal. So you draw something called as reduced zone representation, where this is the first Brillouin zone, and we discussed about it, and you kind of technically fold these bands back into the first Brillouin zone, which is here, and you draw these bands, and you get something like this, which is the EK curve in the first Brillouin zone along something called as gamma point. Maybe let's call it this as X point. And we have discussed what these gamma and X points are briefly. These are the different directions in the crystal, and you can know more about them by understanding about the Miller indices. Okay, so this is the gamma point where K is equivalent to 0. All right. So what we have now here is that we get this reduced zone representation. Okay. Now what happens is that we understood that these are the inner orbitals where there are electrons and they don't take part in conduction. They don't take part in conduction. And we are mostly deal with the electrons present here, where if you apply, let's say, a field, the electrons kind of move in this direction, and there's a hole formed, which is basically a vacant state. The electron goes in the up above state, where you call the bottom of this as conduction band, you call the maximum of this as valence band, and you get the conduction band and valence band picture. Now all of the conductivity which is happening here is happening in this particular band, and mostly we are concerned about the things happening at this particular points near the almost k equals to 0 or Brillouin zone. And when you go further into it, what we studied is that just to revise what we studied, what we did is that we then used this particular concept to understand the carrier transport, which was in the previous week, the carrier transport. Now you have understood that what happens you have understood the energy versus the k space. You can extrapolate it into energy versus the real space, and now you want to know what is happening to an electron inside a real crystal. Okay, so then you studied something like something called as drift. You studied about diffusion. You studied about the Hole current. You studied about the electron current. You studied about the Poisson equation. And in order to fully capture the carrier dynamics inside the device, you need to solve the drift, diffusion, Poisson equation, something called as self-consistently. What do you mean by self-consistent is that you need to solve those equations in a consistent fashion. Let's say you have a drift velocity. You have the drift part, you have the diffusion part, you have the current due to the drift part is something given by q dn by dx. Oops. The current is q times q dn by dx plus nope, it's not this. The current, because of the drift first, right, because of the diffusion from the Fick's law directly, it comes out to be equivalent to q times the dn by dx plus q times dp by dx. So I guess there is a dn here, diffusion constant, and now here is nq mu e plus pq mu e. Okay, so this is the diffusion current, this is the drift current, and then there is Poisson equation, which is something like this. Okay, now what you need to understand is that in this case, in the real space, you get a band diagram, not a band structure. This is the band structure, this is the band diagram. I have been emphasizing on this point quite often because people are very confused about it. So you draw the band diagram, what is happening to an electron in a real space, and what happens is that you understood that these particular, when let's say an electron is moving in this direction, or whenever the electric field is applied, if you want to understand what is happening to the dynamics of the electron, you need to solve these equations, and these equations are going to tell you about it. And there is one more thing in addition to it. There is something called as, let's say, a rate equation, which tells you about, which is something like this: plus generation minus the recombination. Let's write it in general. Generation plus recombination. I guess there is some factor in front of it. Let's call it A. You need to solve the rate equation for the electron. You need to solve the rate equation for the hole in order to understand to the what is happening to electrons and holes as a function of time in a, let's say, if you want to solve a transient problem, something which is time dependent. But if you want to solve these in a steady state means if you have perturbed the system and then you have waited long enough for the system to stabilize, then you are measuring. This is the steady state. This is the transient. Here, the in the transient, the things are varying with time. Vary with time. So this is the time axis. This is, and if you want to solve these in steady state, you just put dn by dt equals to 0, you put dp by dt equals to 0, and you get these particular terms. Let's say for electron, you get a d square n by dx square. I guess this is a diffusion constant, dn, and plus g minus r equals to 0. Then you can write d square n over dx square equals to minus g divided by dn. Let's say recombination equals to 0. If you want to see what is happening to a, let's say, if you irradiate a semiconducting material with a light and some generation is happening, let's say electron hole pairs are generated, electrons are generated and holes are generated. Then if you want to see how they are spatially moving, how they are spatially kind of diffusing, and what is their motion like, you need to solve these equations. They are telling you what is happening to an electron. If you want to solve it fully, what is happening in time also, then you have to solve this particular equation in time, which shows the variation of the concentration in the time. Okay, so this you can even solve analytically, even using certain approximations. By analytically, what do I mean by analytically? Let's say there is some generation function, then you can solve this differential equation, but just by using certain approximations. But if you want to solve it fully, then you can go for something called as numerical solution. Numerical solution. Let's not go into that particular thing here because it's not a course about semiconductor modeling. So this is the particular thing that you need to understand, that this particular flow where we started from and where we have gone till now. And now what is going to happen? This we considered here as a single semiconductor chunk, a single bar of semiconductor. Now we advanced it and we say that let's now do one thing. Let's combine two semiconductor chunks. Let's say one is p side, let's say one is n side. Here we had only a single chunk, a single semiconductor. Okay, now what we do is that we combine two semiconductors P and N. We dope this with as something called as acceptor type impurities. We dope with this side as something called as donor type impurities. And as a result of it, you get positive charge, positive ions with the excess electrons, negative ions with the hole. This will go here, the holes will go here. You will get a depletion region. Basically, they move because of the difference in the Fermi levels, what you might have studied already. So there is a space charge region formed here. Space charge region I have highlighted in the previous lectures also. This is called a space charge region. And these are basically immobile ions. Immobile ions. Okay. And they don't take a part in conduction, but they give rise to something called as inbuilt field, built-in field, which gives rise to a built-in potential. Because there are positive and negative charges, they are separated in space. So this is, let's say, the WD, which is the depletion region, and it gives rise to a built-in electric field. And because of that, there's a built-in potential. And because of built-in potential, now instead of a flat band in the band diagram, you have a bend in the band diagram, because that is what energy band diagram is basically representing the electrostatic potential energy of an electron. When you draw like this, you are drawing electrostatic potential energy of electron on this axis, you are drawing a spatial dimension on this axis, a space dimension. So when you are, let's say, putting some charge here, let's say a positive charge on here, you are putting negative charge on here, you are perturbing this band diagram, because of which the electrostatic potential energy of electron is now going to change. It's now going to shift. How that shifts, we draw it by drawing something called as band diagram. If you had earlier the p side, you had earlier the n side, you had the intrinsic level, you had the Fermi level near the valence band, you had the intrinsic level in the middle, you had the Fermi level near the conduction band of the n side. Then let's highlight the Fermi level like these. That because the Fermi level here is greater than the Fermi level on the p side, it's on the higher end. So it is just like two water reservoirs. So if you have a water reservoir here, you have a water reservoir here, where this is the water reservoir on this side, and this is the water reservoir on this side. Then if there is a barrier in between that water reservoir, then if you open this barrier, naturally this particular side will want to go to the other side. And that is what the kind of concept of Fermi level is. It's just like the highest kind of water level inside the container. It's a very crude kind of definition, but that is what how you can kind of relate it to the mechanical systems. And the water somehow some water starts to flow because there's more potential energy on this side. It wants to go here till the Fermi levels go flat, till both the levels go kind of they align, and at equilibrium both the levels will be same. It will not be at the level drawn by this purple, but it will be somewhere around this thing. So the Fermi level wants to be aligned, and you get from this picture to a single Fermi level, which is drawn by red. You draw it EF. But what happens is that this will go up, this will go down to align the Fermi level on the both of the sides are going to align. But in the bulk, they are going to remain as n-type, as the material they were or earlier. So this will remain n-type. Oops. So this is going to remain p-type. This is going to remain. Okay, what happened? Okay, so let me just rub this. It's not responding. Just a second. Okay, so there will be a common Fermi level, and it is going to, oh god, it's going to be something like this. In the bulk, this is the Fermi level, this is the valence band, this is the conduction band on the p side, and it's going to be something like this here on the n side. That means on the bulk, it remains as it was earlier. The bulk material remains, but what happens is that somewhere here there is a bending. Somewhere here there's a bending. Why? Because there are now those positive charges here, the space charge region. There are negative charges here, and it sets up a field in this direction, electric field. And because of which there's a built-in potential, which is basically the electric field times the depletion width, approximately. Because field is the potential over that particular distance. And now what happens is that you see that what happens actually is that these when you consider these negative charges here, negative ions, on this side they have raised the potential energy of the electrons, and negative ions, positive ions here have kind of lowered the potential energy of here. This is because if you consider kind of, let's say there was an electron, then now if electron wants to come near to that particular charge, it has to spend more energy in going to that region. Okay, so this particular kind of, it has raised the potential energy at this particular region. Whenever you place the negative charge here, you raise the potential energy of that electron, because negative electron and the negative ion, they are going to interact in a different way than a negative electron and a positive ion. So that's why there is a change in the electrostatic potential energy of the electron, just from the basic electrostatics, what you might have studied from in class 10 plus 2 maybe. So that's how the band bending occurs, and that's what the band bending actually determines. Then what we saw is that just 10 more minutes and we will directly jump to the problems, but I want to make the ground. Then what we saw is that when you have this particular bending, the Fermi level is like this, Fermi level is like this, and you have this particular bending, and this is the space charge region. You have space charge region. So these are the positive ions, these are the negative ions. This is the p side, this is the n side, and let me draw it fully. Now, what happens is that if you want to, this is an equilibrium. This is an equilibrium means you have connected these two semiconducting materials, and the moment you connected, the equilibrium is set up. It happens instantaneously when the two material when a diode is fabricated, and it just the space charge region gets formed, and then there is a kind of very minimal movement of the electrons from n side to p side, and holes from p side to n side. Because of this particular electric field developed, it kind of hampers the motion of that particular those charges, and it acts like a barrier here. And what happens basically is that now how do you make these particular things to conduct? We studied in the last lecture, which I told in the last lecture, that there's a distribution of electrons on this side. This is the distribution of electrons which comes from the Fermi function and the density of states. This is n of e, which comes from the multiplication of the Fermi function and the density of states. Okay, so it's something like this, and then it exponentially drops. And then again, then the same thing is on this side. Now you see that if you draw a level here, you see that these particular electrons, they only these particular electrons have energy greater than the purple barrier, and they are going to kind of go through the barrier to the other side, no matter kind of what happens. The only way to stop them is to maybe kind of reduce the barrier more and increase the barrier on the other side. But these are something called as hot electrons or Fermi electrons. This is something called as Fermi tail. They are always there to go to the other side. So what happens is that now what we do when we apply the voltage. Now we know that this is the distribution of electron on this side, this is the distribution of electron on the other side. But very few electrons are here which can normally go on the other side, and they don't constitute a significant part of the current. Okay, so what happens is that now you apply this is no bias condition. Now what happens is that you apply a bias. Now under a bias condition, let's say you connected a positive to the p side and negative to the n side. Then what you are basically doing when you are connecting a positive on this side and negative on this side, you are lowering the potential energy on this side, potential energy of electron, and you are raising the potential energy on this side. And so technically you are just playing with the barrier. You are only playing with this particular thing. You are modulating the barrier. That's all you are doing. The electrons already had that particular distribution that it can go across the barrier, over the barrier. But it didn't because there was a barrier up to this purple level. Now you are kind of raising this particular barrier. Now more number of electrons are going to come out from the Fermi distribution. Let's say if we duplicate this, if we duplicate it here, okay, let's say, okay, let's draw it again. Now the bending will look like something like this because you have reduced the barrier. You have reduced the barrier, and this will be here. This will be here. There will be splitting of Fermi levels now. Why? Because now it's not in an equilibrium. It's not in equilibrium at all because you have applied a potential, and there is a movement of the electrons and holes from one side to the other. Now see what happens is that if you just again see this particular electronic distribution, the particular area under this region has increased. That means N of E is more now, and these N of E can just go on the other side. That means you are just modulating the barrier, and the electrons already are in that reservoir. So they go to the other side of the barrier and play a role in conduction. So
When voltage is applied, sir.
yes, voltage is applied. Just give me a second. I close the window. It's raining heavily here. Yeah, so this is when the voltage is applied, it does not happen by its own. That's why it is a non-equilibrium situation. In equilibrium, very few electrons, which I have showed in here, something called as Fermi tail, they are able to go on the other side, but they don't constitute a current in the diode. But when you apply the voltage, you kind of drop the barrier on one side, raise the barrier on other side. More electrons come out from that Fermi kind of region, and more electrons uh, are now present in that particular end of the tail. Those electrons can directly go to the other side of the barrier, because you see this particular energy is now those electrons which have energy greater than the purple level, greater than this barrier which is shown in purple, they are going to cross the barrier easily, and that is what constitutes the conduction. And similar thing happens with the holes on this side. There is a distribution of holes over this side, and they can move to the other end. It constitutes a current. That means electron goes this way, the holes goes this way, and we say that there's an overall diode current. And then you write those diode equations, which is I naught e to the power qb over kt minus 1. Now, why this diode equation comes, that's a different topic. Maybe professor might have taught about why this exponential dependence comes up and why it's exponential of the voltage, why it does not linearly increase with the voltage. It's because all of the concentrations, electrons, and the holes are exponentially depending on each other. It's exponentially depending on these levels, Fermi levels, and other things. That's why this particular exponential comes. But you might study that in the future. But you see that there is a splitting of the Fermi level. Now you have quasi Fermi levels. Now, the concept of quasi-Fermi levels is something which most people have not understood, I guess. But the quasi-Fermi level only comes into picture when you have a non-equilibrium situation. You don't talk about quasi-Fermi levels in equilibrium. Just like if you showed the two semiconductors in the equilibrium case, you had a single Fermi level. You represent that as EF. You don't you don't draw EFP on this side and EFN on this side, because anyways EFP is equivalent to EFN is equivalent to EF in the equilibrium case. But when you are under non-equilibrium condition, when there is a splitting of the Fermi levels like this, so then you have the Fermi level of electrons as separate and the Fermi levels of holes as separate, because they are under highly non-equilibrium conditions. There is generation of more electrons, there is generation of more holes, so you can no longer apply that particular equilibrium condition. Then you have the kind of quasi-Fermi levels, and it behaves something like this in the neutral region. And this is a overall schematic of the quasi-Fermi levels, because what happens is that you have a
You
question.
just get, you just get like a slope uh, uh, minus ek by 2k. Sorry.
Sorry.
Just get slope in this level, Fermi level.
Your voice is breaking actually. I'm not able to clearly hear you. You want to ask any question?
Uh, just that get uh, in Fermi level, so just like slope and
This one.
uh, yes, sir.
Okay, that is the actual. This is a very, I should say, a very, what should I say? A topic
And so
or a region where people are mostly confused about. And if you understand this thing when you kind of numerically simulate the particular diode or the particular electrostatics of a diode. But I will tell you in a layman sense, what happens is that most of the diffusion thing is, or the electrons and holes are diffusing or the conduction, I should say the current is flowing at these particular regions where there is a where the barrier is basically ending. So that's why there is a kind of slope, and it finally joins their own Fermi level. So that's why this particular slope comes. Because you see that when the electrons are when the electrons are going from this end to the this end, and holes are going from this end to the this end. So most of the processes take place at these regions where there is a kind of where these two particular regions meet with the other region. So you see that most of the processes happen at these two particular ends. So that's why there is a kind of I should say a slope in the quasi-Fermi level. But to deeply understand it, you need to basically simulate this particular entire process. That's how you will get this particular slope. Otherwise, if you see most of the books don't even show the Fermi level inside depletion region. They show like this, they show like this, they say that this is EFN, this is EFP, that's it. But they don't care about what happens to a Fermi level inside a depletion region. Okay, and to understand what happens to a Fermi level inside a depletion region, you need to particularly go through all of that electrostatic equations in order to understand and particularly to simulate this process. And then you will be able to understand that the main processes are happening at these two particular edges where there is a kind of slope in the Fermi level. This particular slope in the Fermi level. It's a very good question actually, and I was hoping that you would somebody would ask at least this question. So that's why these two particular slopes in the Fermi levels come. And why these two slopes come, there is a very kind of, I don't want to go into that detail again right now here. But I have drawn them by intention because
Even
I
I
knew
can
that
see
you would ask.
here in this book. So I can see here in this book the slope is minus Eg by 2k, where
Slope,
then uh,
how much is the slope?
minus Eg by 2k. Uh,
Minus Eg by 2k.
yes, sir.
What is k? It's Boltzmann constant.
Boltzmann uh, constant.
Oh, okay. Yeah. Which book you are following?
Yes, sir. I am following the fundamental of solid state physics. Pragati Prakash. Sir.
Okay, I don't know about this book, but if you see most of the, let's say, Benji Streetman, or if you see any of the other books, they mostly won't show mostly don't show the quasi-Fermi levels in the depletion region, because if you need to feel it particularly what is going to happen, you definitely need to kind of uh, simulate it and understand that when you do this, when you do simulate it, you understand that most of the processes are happening at these particular regions where there is a slope in the Fermi level, because in the end this particular thing is going to give you the let's say the gradient of this particular thing is going to give you the field. And then this particular picture directly comes from the electrons and the holes being getting out of that region at these two particular regions. That's why whenever you these regions are also important, because whenever you solve the current equation, you either consider to solve at this region or this region. You don't solve anywhere at a random position in a diode when you derive this current equation. I naught e to the power q
Okay.
v over kt minus
Okay, sir.
1.
Thank you, sir.
So
Okay, sir.
because when you if you see how the variation of the I should say the charges inside the diode happens. If this is doped with Nd, this is doped with Na. Let's say this is constant. These are both same on the both. These are same on both of the sides. This is Na. This is Nd. Then how the charges behave inside this particular thing is that if the electron goes to the other side, it decays, and this particular decay length is the electron recombination length or the diffusion length. And the holes on the other side, these are the electrons, these are the holes. When they come into the other side, they decay, and the decay length is the diffusion length. And now what happens in the middle? Obviously somewhere in the middle it should be something like this, it should be something like this. Okay, but this is a very this is approximately I'm drawing, but somewhere there should be a crisscross where you have a point where there is a particular crisscross in the concentrations. And this is the case when both are same doped, but you would get a different curve when let's say ND is more greater than NA. Let's say this is for NA equals to ND. But what happens if ND is greater than NA or NA is greater than ND? You will get different types of profiles for the charges. But you see that most of the kind of you see the slope of this is particularly max at these two particular regions. Okay, so it's the point where there is a maximum kind of diffusion happening of these particular charges, and that is reflected in the kind of slope of the quasi-Fermi level to a kind of first order approximation. And when the electron goes to this side, it recombines with the holes. When holes go to this side, it recombines with the electrons. And that's why mostly you want to keep these regions small so that you can at least collect those electrons and the holes. They don't decay away. Okay, and that is the overall summary about it. And and just one last thing I want to actually show is that the real diode is not made like this. This is, I should say, a very basic schematic of a diode. The actual diode is when you fabricate a diode, how it is made. You take a single substrate, let's
Sir,
say
I
N.
may be wrong. I may be
Sorry?
wrong, sir. I may be wrong when I say uh, minus EK by EG by PK.
Huh? What is it?
Minus minus EG by PK. It
Huh?
will be it may be wrong, sir.
I'm not
I
able to clearly hear you, to be honest. If you can write in the chat or message what is the slope of this, but I don't need to know about it. Maybe you can compute it by using some equations. At the end of the day, there will be some equation to that particular line, and you can compute the slope of it. But if you want to write it, you can write it in the chat because your voice is not clearly audible.
okay, sir. Thank you, sir.
Okay, so I wanted to say that if you see this particular thing here, how it is actually made, how the diode is actually made. We take an N substrate, a single substrate, N-type silicon, let's say, N-type silicon, and by using certain processes, you dope it here, and you make a certain region, something called as well, and this particular thing is P-type. So this is what you get. This is where you get a you get a kind of depletion region. You get positive charges around this thing, positive charges around this thing, and you get negative charges around here. So this is the actual structure of a diode, how a diode is made. Then you take the two terminals out. You take this terminal. This is a P type. This is one terminal. This is another terminal. So that's the particular thing you might have seen. You might be seeing in your labs. Two terminal device. This is that how diode is actually available in the market. And the actual picture is something like this. There is a p-type region here, and there is the n-type region there. This is the actual kind of three-dimensional structure. So you see how complicated it is. What you are here showing, this one, this is a very basic schematic. This is the actual schematic. Okay, and this thing will be having certain width also thickness. So this is the actual schematic of it. Now you see that you have the depletion region throughout this particular thing. Okay, so you have to solve the electrostatics accordingly, but we don't care about solving the electrostatics in 3D around this particular thing because the 2D and 1D cases are enough to visual for us to visualize how the carrier concentrations are changing inside the particular diode. But this is the actual representation of the or the how the actual diode is made in real life. So now jumping on to what we have to solve and what we have to see. Now we saw the diode picture. Now let us talk about directly about the questions. Okay, so for the question number one, it is saying that you have to consider an silicon PN junction diode. Now the diode we were discussing, and based on the doping profile, you have to answer the following questions. Again, you have to consider silicon, where this particular thing is doped with Na, this particular thing is doped with this is Nd and this is Na. There is a metallurgical junction and there is a depletion region formed here. Now you see from this particular profile there is a flat line in the Nd. That means this is uniformly doped. This is uniformly doped. It is constant doping throughout this particular region, constant doping. And then you see on the blue side, this is again a constant doping. Now what does this particular thing tell you? This tells you the magnitude of doping, how much doping is done. And this particular thing tells you the magnitude of the Na dopant, how many dopant atoms are being kind of used for doping process. And you see that this particular Na is much, much greater than Nd. That means Nd is less than Na. This is the particular scenario which you get from the graph. Now, if there is any more details, then we can directly jump to the what is the question. The corresponding charge configuration of the p-n junction diode is depicted in which figure? So you have to mention the charge configuration. Which charge configuration is he talking about? He's talking about the depletion charge configuration. Okay, so because Q times, let's say when you have this particular doping densities, these two particular doping densities, there will be a depletion region formed here. And because Q times Nd is much smaller than Q times Na, what is going to happen is that when the depletion region will be formed, more of the depletion region will be towards the N side. This is the N side. And there will be a little depletion region across this side. So this is spreaded more into this is the actual space charge region will look like. And why does this happen is because when you, let's say, made this particular thing, there are positive charges, there is electron, there are negative charges, there are holes. This is N side, this is P side. Because this is lightly doped, this is Nd, this is Na. Because Nd is less than Na, that means there are more number of negative ions or these particular ions on the negative or holes on the P side. And because in this region, when there is a metallurgical junction where you have kind of joined the two regions, P and N side, you have to maintain the charge neutrality. Charge neutrality means that the charges on this side should be equivalent to charges on this side. That is only going to happen when, let's say, holes are here and you have only two electrons. Or let's say you have only, no, let's not talk about these. Let's say you have two ions and you have two ions of this particular thing. Or let's say you have three ions. What is going to happen is that because this particular area is very lightly doped than that of the other case. In order to find the equivalent number of positive charges, the negative charges will kind of need more positive charges on the N side to kind of balance their particular field. Okay, because let's say if this would have been equally doped, then equal number of kind of charges we are going to be to occur at the space charge region. The charges are the depletion width is going to be same on both of the sides. Now, because this region is highly doped, then the negative ions kind of go deeper into the N side in order to balance them because it's not able to find same number of positive charges near the metallurgical junction. So it goes deeper into the N region to find the same equal number of positive charges to balance them. So that is why there is a more depletion region around this region. Depletion width is more on the other side than on the P side in order to maintain the charge neutrality. I hope I didn't confuse you, but maybe I kind of said a very large statement. So if you have, let's say, negative ions on this side, then it looks something like this on the N side because there are less number of kind of these dopant atoms as compared to that on the P side. So in order to maintain because the neutrality has to be maintained, so negative charges require kind of the in order to neutralize them, they kind of go deeper into the n side in order to balance them. So that's why this region spreads on the n side more as compared to that of the p side. Okay, just to maintain the neutrality, because what happens is, because if there is a positive charge, then for the electric field to kind of terminate, there has to be a negative charge. But if there is one more negative charge, then electric field lines will look something more like this. So there, if let's say the if let's say you have to maintain the charge neutrality on both of the sides, there should be equal number of charges on this side and this side. So that is what the kind of statement also again refines to the fact that you have to have more number of charges on the n side and less number of charges on the you have more number of kind of more spreaded region on the n side and less spreaded region on the p side. So that boils down to the fact that this particular charge density should look something not like this, not like this, not like this. It should look something like this because the region is spreaded more onto the n side. It's like negative ion is looking for positive ions, but because there are less positive ions, it goes deeper into the n side to find same number of positive charges. Okay, in order to balance them. That's it. That's the simplest thing. These are negatives, these are positive ions. That's it. The simplest. So what happens again now? I think this second part is related to it also. Now you have to find the electric field. Just because there is a neutral region, there will be electric field developed in this direction. We know that electric field is from the positive to negative charges. These are positive charges, these are negative charges. Now, what will be the electric field profile? For that, you need to simply solve the Poisson equation. You have this particular thing is equivalent to the rho over the epsilon silicon, if this is silicon, and this is particularly epsilon naught epsilon r, and you know the values of each. But what how we need to find the electric field is here. Electric field will be equivalent to some integral of rho over epsilon silicon into dx, let's say from x1 to x2, plus there will be some integration constant, let's say c. Then how we are going to solve this is now a simple mathematical problem. You have a function, you have a function like this, and you have a function like this. This particular function is, let's say, it is up to xn, and this is q times nd now. Okay, so and this particular thing is q times na. And now what happens is that you need to solve this particular integral in order to get the electric field. Just you need to put the rho equals to q times nd. Let's say if you solve for the red region, you get E electric field to be equivalent to, let's say this particular point is 0, this is xn, this direction is x. Let me solve it something like this. Let's say we do the integral from 0 to x some x, and rho is q times nd divided by epsilon silicon. Let's say this is dx dash, a different variable maybe, plus some integration constant, which will be we can obtain this from the boundary conditions or the conditions which will be given in the question. We will see it. So electric field we get as q and d x dash divided by epsilon silicon from 0 to x plus c. When you put the limits, you get q and d x divided by epsilon silicon plus the constant. And how you obtain this? Because this is electric field as a function of x, and you know that electric field at x equals to xn is equivalent to 0, because there are no charges outside this region, so electric field cannot exist in that region particular. To a first order approximation, you will later on see maybe it can exist or maybe it may not, but let's just assume that this particular thing is equivalent to 0, and you get E of x equals to xn equals to 0. You get q and d x n epsilon silicon plus c equals to 0. You get c to be equal to minus q and d x n divided by epsilon silicon. So you get the overall electric field E of x to be equivalent to q and d x epsilon silicon minus q and d x n divided by epsilon silicon. You get q and d over epsilon silicon x minus x of n, which is electric field as a function of x. This you get as a function of x. This is the electric field. Now you just have to plot it, just a y equals to mx plus c type relation, where the slope here would be given by q times nd over epsilon silicon, and this is the particular intercept. This is the intercept. This is the intercept. This particular thing is the slope, and note that the intercept is negative. So it's a straight line with a negative intercept and a positive slope on the region from 0 to xn, this region. So let's see from this region in all of these cases. Let's see where it is. So you have, first of all, you note that the slope is positive in all of the cases, not this one, these three cases. The intercept is negative here, and you see that the particular intercept is the cases look, these three cases look kind of feasible, but how you are going to how you are going to decide about it. So for that you need to solve the electric field along this direction. Now when you solve this using the similar approach, when you solve the electric field again using 0 to, let's say, x q and a divided by epsilon silicon dx dash plus some constant, you will get a profile which will be something like QNA minus QNA epsilon silicon x plus xn. This will be electric field as a function of x for x less than 0, greater than x of p, minus x of p. So this particular thing, when you map, you will get a region here, which is something like this. So you get a field profile which looks something like this, and then something like this. This is just plotting of the straight lines. That's it. Okay, because this will be having negative slope, and the positive negative slope, and again the negative intercept. Okay. So that is the particular profile of the electric field. And this is spreaded more in this region because there are more positive charges in this region. When there are, this is like the scenario is something like this. There are more ions on this side. And there, this is the scenario, the space charge region. This is the space charge region and space charge region. And electric field is in this direction. In this direction, electric field. Okay. So spatially this is more and this is less, so spatially this should be more, this should be less, as simple as that. This cannot be the scenario, this cannot be the scenario, because it's showing both of the spatial regions same. Okay, so the separation between the charges is going to matter for the electric field, definitely. Okay, because from the basic electrostatics you know that how we define the electric field and the forces. The force itself, Coulomb force, is some k q1 q2 divided by r square. And if you write force equals to minus QE, then you can write E equals to minus F by Q. Then you write the electric field as KQ1 divided by R square. And you see that electric field depends upon the distance. That's why this distance is going to matter for the electric field. Okay, so this is the profile of the electric field, and the answer of this particular part should be A. Now Now there is a weird doping profile. Doping profile is how you dope the particular region of a semiconductor. Let's say you have a silicon and you doped it uniformly. Uniformly means same doping throughout. Same doping throughout. That means Nd and A are equal. Equal, as well as the profile means, profile particularly word means the shape of that particular doping. How you are going to place that those dopants inside. Just like I showed, let's say if let's say if you dope, what this particular thing means is that there is a uniformly kind of doping present throughout. It's there is no kind of no weird shape of the doping. There is uniform doping throughout. Now if I dope it, let's say differently, let's say this is a silicon, this is p side, this is n side. If I dope it something like, let's say I dope this region as something like this, and I dope this region something like this. So then this region is doped as something called as linear doping, linearly, and this is like say a Gaussian doping, because this profile almost resembles a Gaussian and this resembles a linear. So this is a profile, means a shape, how you kind of dope these particular regions and what type of shapes they kind of diffuse into it. Okay, and there can be now any shapes in the questions or whatever the physical scenario is. It just depends upon how you solve this particular thing. Rho epsilon dou x, x1 to x2 plus c. You just have to solve this. Considering now it's just a mathematical problem that you need to consider the function of this, you need to consider the function of this particular thing, and whatever the shape will be given for you. Let's say I have a silicon and I dope this region as this, and I dope this region as this. Then this particular doping will be let's say let's consider it a sine doping, sinusoidal doping, and this is again a linear doping. And then you need to put those functions here, solve the integral, you get the field profile as well as the other things you might have to compute. Let's say for this case, the rho of x would something look like e to the power minus x naught square divided by 2x naught, or let's say 2xp, where this x naught will be the center of this Gaussian and the and xp will be the spread of this. Okay, like this. And you need to put this rho of x function here, solve this integral. You better know how to solve it. X1, x2, e to the power minus x naught square, 2xp dx plus c. Solve this particular integral. And how you solve it, that is your kind of headache. There are certain functions, let's call something called as gamma functions and other things which you can use mathematically. Now it all boils down to how good you are at mathematics. And maybe such questions may appear in the examination as well. I don't know. And these are the profiles. Now you have a simplest profile here. You have a linear doping here. So you have a linear doping and you have a uniform doping here. Okay. Now the charge configuration, space charge region is going to look something like this thing. Okay, this is how the space charge region is going to look like, because there will be spatially present charges over here, which will be q times nd, this thing. This will be q times na, this thing. Okay, now you need to find the electric field. Electric field will be obtained. So the answer of this is A. Electric field will be again obtained by the similar procedure which I showed. Consider here the rho of x to be a linear function of x. It is directly proportional to x because it's varying linearly. It's a straight line passing through the origin. Straight line passing through the origin. This is y, this is x. That means y equals to x. That means rho of x is directly proportional to x. Now you need to solve E equals to let's say some x1 to x2. Let's solve from 0 to plus xn region, because this particular region is easy. This is also in the previous part, but this particular region you have to integrate. You write rho of x epsilon silicon dx plus c. You get similarly you get 0 to x of x dash, some x dash. You get q and d of x. This is the particular thing because it's directly proportional to x. It's a function. It's a function where you have something like this. This is q times nd. So this is q and d of x. It's a function y equals to, y equals to mx plus c. Here there is c is 0. So q times nd is the thing. Okay. So you have to integrate with respect to x. You get q and d x squared divided by 2 epsilon silicon 0 to x dash plus c. This is the electric field. And just from the kind of visualization, you got to know that it is electric field is going to vary as x square, which is a parabola. And what happens is that now you have to compute this particular c, again following the similar procedure which I showed in the previous. You are going to obtain a relation. Let's say E at x equals to x equals to x, and again is going to be, you are going to find that particular value, and let's say this is 0, and you're going to obtain the value of the c. Then you are going to see that in this region the electric will be parabolic, a curve like this, and in this region is going to be similar as in the previous question. And the answer of this question is not going to be this, because in this region it cannot be parabolic because the doping is uniform. And this cannot be the answer because here the slope is positive, it should be negative. And this is no way possible because both of these cannot be parabolic. So the only remaining answer is this particular thing. This is parabolic, this is linearly varying. Again, if you just this is just also from the intuition. Okay. And what happens is was if this question would have come in any competitive examination, this was a kind of I should say maybe a 3 second or 5 second problem. How? Because we know if you have a delta function, if you integrate it, you get a unit step function. It's just from signals and systems, basic maths. Everything is going to be utilized in engineering. If you integrate it, you get unit step function with respect to dx. If you integrate it with respect to dx, you get a ramp function. If you integrate this particular thing with respect to dx, you get a parabolic function. As simple as that. If you just kind of, I shouldn't say remember because there is nothing to remember, but if you just understand this thing, you're going to solve these questions in seconds. Now, that means if you have a delta function, if you have a delta doping, something like this, delta function, if you find its electric field, it's going to look something like this, a uniform. If you have a uniform doping, if you find its electric field, you're going to get a ramp. If you have a ramp in doping density, if you integrate it, you're going to get a parabola. Simple as that. Now it's up to you what functions you take. But these are the mostly used functions in the this thing. If you go the reverse way, you have to differentiate with respect to x, differentiate with respect to x, differentiate with respect to x. So that's what it's kind of how I learned or I should say how I used to save time in these questions without, but it just comes from me doing the simple integrals. That's it. But these are the mostly kind of given questions in the competitive examination. Anyone has any question? Somebody just turned on the mic, I guess. Okay, so let's move on to the other question. So the answer of this question is A. Now, what there's a remember and reflect part. Let's read that. The important point to remember is that approximation made to doping profile is sufficient to give us the qualitative understanding of junction behavior. Field profile is futile. It's always good practice to start. You should always know why the field goes to zero at far away from the junction. Okay, so when you do kind of you saw in these particular things that when you draw these things, let's say these are uniformly doped, but the doping is not equal. This is Q times ND, this is Q times NA, and just open the, just give me a second. So these are positive, these are negative. Okay, just a second. So when you draw the field profile, you got something like this. And pretty much you showed that at these particular points, minus xp and plus xn, you showed that the field goes to zero. Uh, is it the case that field goes to zero just outside the space charge region? Pretty much to the first order approximation, this happens, but in a real actual sense, this does not happen because such a field profile, such a charge profile is not possible. You cannot make a such sharp charge profiles in a any structure. There is a spreading always. So this particular charge profile actually something looks like this. There's a spreading. There are various reasons for the spreading, but let's not go into that. But there is spreading. These actually look something like this. And because of that, it's kind of exponentially decaying, and you know that exponentially decaying, it does never touch the x-axis. So basically, electric field pretty much does not kind of totally vanish at the ends. It looks something like this. And that's why these particular ends are very important in modeling when when you model it using numerical techniques. Something something you guys will study in higher courses in semiconductor device modeling. But that's why these regions are called as something called as quasi-neutral regions. Something called as quasi-neutral regions. Why that is the case? Because you consider the electric field to be uh, almost zero, negligible. That's why the word quasi. Word quasi means something is there. But if it would have been a totally neutral region, then we would have just named it as neutral region. But we have named it as quasi-neutral region because there is some influence of the field, and you will see why this field is important in maybe upcoming courses or when you go to the higher classes. This field is really, really important for these particular devices, and that is the maybe the point which the professor wants to mention here. And now moving on to the question 6 and question 9, just numerical questions. Let's quickly go into these questions. So the doping concentrations in abrupt silicon p-n junction. First of all, what is abrupt p-n junction? Abrupt junction is the same thing, which kind of has a something like which has a junction, something like this, abruptly drops. And these abrupt changes are not, these things do not happen in real nature. So that's why I show that this actually something like this. But for the numericals kind of simplification, we show it as abrupt. We show that these changes happen abruptly, very quickly. But this is not actual thing. You don't get these corners in real nature. You don't get these sharp edges in real nature because you know that you cannot differentiate at these particular edges, and you cannot do other. Maybe you might learn that in higher classes. But these sharp edges are not a kind of natural trend. So this is Q times ND, this is Q times NA, this is XN, this is minus XP, this is 0. So these are sharp silicon p-n junction with a sharp profile. And temperature is given, Na is given, Nd is given, Ni is given, the volt equivalent of temperature or the thermal equivalent of temperature is given, permittivity is given, the absolute permittivity and the relative permittivity of the silicon is given, and what we need to find is the depletion width is also given. Okay, we need to find the built-in voltage. Okay, so built-in voltage is simply basically kT ln of the concentration on second side divided by electron concentration on the other side. Maybe you're not aware of this formula, but actually this is the basis. It comes from the derivation. So if there is some concentration on this side, there is some concentration on this side, then you can write it as kT ln of n, let's say nd divided by ni square over na, and you can write it as kt by q ln of na nd divided by ni square. So basically electron concentration here would be ni square over n na. The whole concentration here will be ni square over nd, because these are the minority carriers here, these are the minority carriers on the p side. This is p side, this is n side. So this is the equation you need to use in order to compute the built-in voltage. And everything has been given. Let's see what it comes out to be. The kT by Q is volt equivalent of temperature, which is 26 milli, 26 milli, 25 has been given, 25 millivolts. And note that here, don't get confused. Sometimes kT is only given. That is given in 25 milli electron volt. This electron comes because of Q charge. But if you have kT by Q, then this is 25 millivolt only, because that E has gone absorbed in this Q. Q is basically the electron charge. Just kind of take care of this. So you are given KT by Q, and so you have built-in voltage to be 25 into 10 to the power minus 3 natural log of Na and D are given everything 10 to the power 16 plus 10 to the power 12 divided by 10 to the power Ni square is 20. You get 25 into 10 to the power minus 3 ln of this is how much? I guess 28. So 10 to the power 28 minus 20. This 20 will go, the 20 will go up. It will become minus 25 into 10 to the power minus 3 natural log of 10 to the power 8. So you can write it as 25 10 to the power minus 3, 8 ln of 10. So this is 2.31 into 8, 25 into 10 to the power minus 3. You solve this, you get 0.46 as the answer. Let's roughly solve it. How much is 25 into 8? Okay, I think it's 200 into 2.31. Okay, let's 200 into 2 is 4. So somehow they'll come 400. And वही आ जाएगा, ठीक है. So the answer is 0.46. Because there is 10 to the power minus 3, it will become 0.4, so you get the answer. Okay, so this is about the question. So you get built-in voltage to be 0.4 volts, 46 volts. What's the other question? The other question is depletion width on the N side of the PN junction. Now you know from this particular problem, note that here this profile I have not drawn to the scale as per the question, because actually the ND is much greater than NA in this question. So this should actually look like if this should look like this, and this should look like this. It should be lower than this point. Okay, so actually it should look like this should be the Q times ND. This should be the minus Q times NA, and this particular thing is lower than is less than that of the other thing, because ND is given much greater than NA. Okay, so this is the actual thing. These are the positive, these are the negative things. Now we need to find the depletion rate on the N side. Okay, so N was ND given greater? Yeah. So depletion region on the N side, because we know from the previous concept that if this region is highly doped and this region is lightly doped, then the depletion region penetrates towards the lightly doped region in order to neutralize the atoms, neutralize the number of positive and negative charges. So there will be more negative on this side. It will be more spread on this side, and there'll be less kind of positive charges on this side. So rather I should show it like this. It is less, but it is spread more here. This thing is more, this thing is less. You have to take care of everything. You have to take care of space as well as the y-axis. Okay, so this is the actual thing. So we know that this is n side, this is p side. So we know that this should be less than that of this spread. So the region, space charge region will be less penetrated towards the N side and more penetrated towards the P side. Okay, because of maintaining the neutrality, space charge neutrality. All right. So we have to find the depletion region width. Okay, we know that if this is XP, this is XN, then XP plus XN is equivalent to overall depletion width. That is this thing, depletion width. And I guess depletion width is given as how much it is 24.6 micrometers, 24.6 micrometers. Then we can write xp plus xn equals to 24.6 micrometers. Okay, we have this equation, but we have two variables. We need maybe another equation, or we need to replace one variable in terms of another. How we are going to do it? We know that because of neutrality at this particular region, there will be equal number of, or I should say the field should be equal at these two particular regions. We can write it as QND XN divided by epsilon silicon should be equivalent to QNA XP divided by epsilon silicon. these things will go, and uh, you can get ndxn equals to naxp, or you get xn divided by xp equals to na divided by nd. So we need to find what? We need to find on the n side. So let's write xp as ndxn divided by xa and put it here. So you get xp plus xn is 24.6 micrometers. When you replace xp by ndxn divided by, this is na plus xn equals to 24.6 micrometers. Now you get xn, nd by na plus 1 equals to 24.6 micrometers. You get xn to be equivalent to 24.6 micrometers divided by nd plus na uh, divided by na. You get 24.6 into na divided by nd plus na, just doing more number of steps. But because we know nd is much greater than na, so we can replace the denominator by just nd, 24.6 divided by nd into na. So it will be 24.6 into 10 to the power 12 divided by 10 to the power, how much was it? 16, 10 to the power 16. You get 24.6 into 10 to the power minus 4. So this was in micrometers, remember. So this is 24.6 in 10 to the power minus 6 meters into 10 to the power minus 4, ye wala. And you get 24.6 in 10 to the power minus 10 meters, which is 2.46 nanometer. See how smaller the region of space charge is. This is approximately 2.46 nanometers out of 24.6 micrometers. Overall depletion width was 24.6 micrometer, but the depletion width is spread in X region, in N side, about only 2.4 nanometers, which is very, very, very small. And the rest of the thing is spread on the P side. Okay, so the answer should be 2.46 nanometer. Okay, okay, this has to be in micrometers, so this is the answer of this question. 2.46 in 10 to the power 3 minus 3 micrometers, so it will be nanometers. Yeah, that's the answer of this question. It's a very smaller length. To physically show how kind of small this length is, if this is N side, this is P side, and if this is the metallurgical junction where the two regions are physically in contact and space charge region is formed, then let me show the exaggerated version of this, how the space charge would kind of look like in actual device, because of the kind of significant difference in the dimensions of the space charge region on the N side and the P side. This will be 2.46 nanometer, and this will be rest of it. Matlab 24.6 micrometer minus 2.46 nanometer. And this is almost 24.6 is on the P side. It is negligible. You are subtracting 2.46 nanometer from micrometer. It's as if it means same. That's the I think the other the second part is, what is the depletion width on the P side? So you have to subtract 24.6 micrometer minus 2.46 nanometers. And it will be almost approximately 24.6 micrometers, which is this part. Okay, so because xn plus xp is w, so xp will be w minus xn. So that's where this thing comes from. All right, let's move to the next question. Does anyone have any question or anything? Okay, If not, then let's move to the other part in the same spirit, and I think it's related to the same question. We have to find the magnitude of electric field. And we can find the magnitude of electric field again. We know the profile looks something like this. It looks something like this. This is the actual profile, how it will look like. Now, because we have found this region is 2.46 nanometer, and this is the 24.59 micrometer, जितना बाकी जो बचा है, and the overall is 24.6 micrometers, W, which is the depletion region width. And if you draw the electric field profile of this, that will look something like now it should be easy for you. It will be spread more here because these are uniformly doped. It will be very little part here. This should be the electric field. This is Xn, this is 0, this is minus Xp. And you have to find the magnitude of electric field. That means magnitude of this E max. And roughly it's equivalent to twice the built-in potential divided by the depletion width. Roughly. You can choose the same thing. You get, let's say, 2 times the built-in potential. Where is that? Actually, it comes from the taking the built-in potential, depletion width divided by 2. This 2 goes up and you get the same thing. How much it was the built-in potential? I think it was 0.46. And W depletion was 24.6 micrometers. You get 2612, 2489, oops, 0.92 over 24.6 into 10 to the power minus 6, oops, plus 6. You solved it, you get, should you get the same answer? Or there is some mistake? Or maybe if this thing, maybe there might be some error here, but you can anyways use the electric field as the integral of x1, x2. Let's go to the basic conventional way, rho x. Whenever something doesn't work, you should always go back to the basic maths because that will work. Plus some constant. You solved for this particular case and you got q and d x n divided by epsilon, and this is the electric field on the n side. Electric field on the p side was q n a x p divided by epsilon silicon. Okay, yeah, I think you will get the answer from these two questions. You will get the answer from these. You use these particular things and you get magnitude of electric field. Overall magnitude will be 2 times the q and d x n divided by epsilon silicon. There it will be maybe 1.6 and 10 to the power minus 19 into, let's use nd 10 to the power 16. This is per centimeter cube. We need to convert it into meter cube. That'll be 10 to the power 6 minus 6 meter cube per meter cube. Is it correct? Oh god. Okay, I think this is fine. Per centimeter cube. So it'll be 110 to the power minus 6 per meter cube. Oh, not meter cube. This will be 10 to the power 6 meter cube. Per meter cube, sorry. 10 to the power 6 per meter cube. 10 to the power 6 per meter cube. And you found this thing, it was 2.46 in 10 to the power minus 9 meters, nanometer. And the epsilon, it's a very huge calculation. Epsilon naught into 8.85 into 10 to the power minus 14. I think it's farad per centimeter. This thing is given as 11.9 and just take it as approximately as 12. And yeah, I think it will give you the answer. Minus 19 plus 16 plus 22 minus 9 divided plus 14. How much is that? This will be 3 minus 9. This will be minus 7 plus 14. This will give you 7. Okay, the other things would cancel out from this. Roughly it will come out to be 3.73 10 to the power 2. And there is a 2 factor here. Exactly. Okay, so doing the same approach, you are going to get the magnitude of the electric, but note that it has to be mentioned in volt per centimeter. I guess you have to change here There is no need to change here from centimeter to meter because everything has to be kept in centimeter. That's why maybe the sort of magnitude error has been there. This is of the order. So when you reduce it back to from meter cube meter to centimeter, you have to multiply it accordingly. That's why there was a magnitude error. Okay, so this has to be in centimeter. So you get the electric field, and there is a reflectant. Remember something professor has given here. The above problem demonstrates that when a p-n junction is heavily doped on one side, majority of depletion region. Okay, that's what we have discussed. That majority of the depletion region will be on the blue side, and it's almost as if entire depletion region is on the p side. That's it. Now the question number 9, what it says is that we have to. It's a very good question, I guess, because there is same doping on both of the sides, and we have to consider it is an isotype junction. Isotype junction means a junction which is formed of the same type of material. Just like this is p-type, this is p-type, but what is the difference? There is a doping difference. This thing is more doped, Na1. This is less doped, Na2. That means Na1 is greater than much greater than Na2. And what is going to happen is that there will be still a barrier formed. Why would there be a barrier formed? Because let's consider this to be one side, this to be other side. Isotype, p side, p side. This is the intrinsic level, same, because Na1 is greater than Na2. This is P2, this is P1. What is going to happen? There will be more holes present here in this system. More holes, less holes. As a result of this, the Fermi level is going to be much closer to the valence band in this case, and it will be slightly above the valence band in this case because there are less holes in this case. The Fermi level, more closer it is to the valence band, it is showing more number of those particular types of carriers. If it is more closer to the conduction band, more number of electrons in that system. If it is more closer to the valence band, more number of holes in that system. Just like that. So this is the Fermi level. Fermi level. Note here, I'm not showing quasi Fermi level because quasi is not applicable here. It's just Fermi level. Don't get confused with it. It's a Fermi level of p-type, Fermi level of n-type. And when you combine it, what's going to happen is because all of this energy is with respect to electron, whatever we draw. So if you are drawing this particular Fermi level higher here, that means what is going to happen is that electrons are going from this region to this region, and hole will come from this region to this region. Because for holes, everything what happens for the electron in this band diagram, opposite happens for the holes. And we draw this band diagram with respect to electron, not with respect to hole. For hole, we consider everything to be opposite. We draw it with respect to electron energy. So when there will be motion of electrons, because electrons are anyways going to be present in the system, although they will be less, but they are going to be present in the system. Because if it is totally p-type, then you know that the electrons will be minority carriers, but they are there. Minority carriers means you can find the concentration to be equivalent to Ni square over the Na, Na1, and here this, let's say it's N1. They also, the electrons on the p1 side, let's not confuse because I have used the notation p2 here, p1 here. So this is N2, this is Na2, and this is N1. It will be Ni square divided by Na1. Okay, and because Na1 is greater than Na2, that means N2 will be greater than N1. That means there are more electrons on this side. There are more electrons, less electrons. Or in other words, you can say there are less holes here, more holes here. If there are more holes here, hole will go from this side to this side. If there are more electrons here, electron will go from this side to this side. In that process, what is going to happen? the electronic potential energy diagram is going to change. When the electron will move from this region to this region, here at this particular point, the electron's potential energy is going to increase now because more negative charge is going to come at this place because of the movement of electron from this region to the purple region. So electron की potential energy rises. It means that if now other electrons want to come near the purple region, they have to spend more energy to get closer to it because already electrons have increased the potential energy of it. It is like if electron comes here, it raises the potential energy of it. It means that if other electrons now want to come here, they have to face this potential energy. They have to spend more energy to remain at this particular region. And that is reflected in the band diagram. That means इसकी band diagram जो है, it will look something like this. Okay. So that is this particular thing. It's the same concept in PN diagram. That's what the band diagrams depict actually. So once this happens, if the electron goes from this to this region, the Fermi levels want to be kind of aligned. They want to be aligned. This will move down, this will move up, and the picture will look something like this. Single Fermi level and intrinsic level is something shown in the middle. This is the entire scenario. Okay,
Sir,
and
when this change, then the band diagram will be changed.
when
When this change, p-type, n-type, then band diagram will be changed graphically.
I'm not getting your question, to be honest. I mean, I'm not able to hear you clearly. Either you speak louder or I think I should increase the volume. Yeah, tell me now.
Sir, uh,
Just
uh,
just a second.
where p-type, n-type alternative change.
Sanjeev, just a second. Are you comfortable in speaking in Hindi or Urdu or any language?
Ye- Yes, sir, Hindi.
Yeah, you can just tell me. Just हिंदी में बता सकते हो.
सर इधर पी टाइप एन टाइप चेंज हो रहा है
हम्म. यहाँ एन टाइप है ही
तो
नहीं. पहली बात यहाँ एन टाइप नहीं है. ये दोनों पी टाइप है. इसीलिए ये क्वेश्चन अच्छा था, यूनिक है. बट
ओ
यहाँ
अच्छा सर
दोनों पी टाइप होने के बाद भी ये पी टाइप है, ये भी पी टाइप है. दोनों पी टाइप होने के बाद भी डिफ्यूजन वो होगा, इलेक्ट्रॉन्स का भी होल्स का भी. ऑल्दो वो कम इलेक्ट्रॉन्स है, बट इट्स लाइक ये होल्स मूव कर रहे हैं. उसी का मतलब है कि इलेक्ट्रॉन दूसरे साइड से जा रहे हैं. और उसकी वजह वजह से क्या होगा कि ये जो पर्पल वाला रीजन है, यहाँ पे जो पोटेंशियल एनर्जी है इलेक्ट्रॉन की, वो राइज हो जाएगी क्योंकि वहां पे इलेक्ट्रॉन गया. तो कोई भी और इलेक्ट्रॉन आने के लिए उस इलेक्ट्रॉन को ज्यादा एनर्जी स्पेंड करनी है वहां रहने के लिए. उसी का मतलब है कि इलेक्ट्रॉन की पोटेंशियल एनर्जी इंक्रीज होगी वहां पे. अब तो अब कोई और इलेक्ट्रॉन अगर आएगा तो उसको बहुत एनर्जी स्पेंड करनी है वहां रहने के लिए, क्योंकि इलेक्ट्रॉन इलेक्ट्रॉन रिपेल करेंगे. तो इसी का मतलब है कि पोटेंशियल एनर्जी राइज हो गई. ये दिखा रहा है ना, इसका मतलब वही है कि पोटेंशियल एनर्जी इंक्रीज हो गई. तो
अच्छा
यही
सर
यही चीज नॉर्मल पी एन डायोड में भी होता है. तो अब अगर ये राइज हो गया तो ये एक हिल टाइप बन गया इलेक्ट्रॉन के लिए. तो इसका मतलब ये जो बैंड डायग्राम है इट विल लुक समथिंग लाइक दिस. ओके. सो
ओके
दिस
सर
इज द ओवरऑल कॉन्सेप्ट ऑफ इट. गॉट इट.
गॉट इट सर
ओके. So now the final question. ये कुछ something there is one important point to remember is that there are no donor atoms present. इसमें इस सिस्टम में कोई डोनर एटम नहीं था क्योंकि ये दोनों दोनों पी टाइप थे. पी टाइप थे. यहाँ भी Na था, यहाँ भी Na था. And here the whole concentration is in excess as compared to this. यहाँ पे बहुत सारे होल्स थे, यहाँ पे कम होल्स थे, इसीलिए होल का ये हो गया, डिफ्यूजन हो गया, ये यहाँ से यहाँ. और इलेक्ट्रॉन, उसी का मतलब है कि टेक्निकली इलेक्ट्रॉन यहाँ से यहाँ गया. उसी का मतलब उल्टा ये हो सकता है कि होल दूसरी साइड से गया बिकॉज इट इज जस्ट द वेकेंसी, वेकेंट ऑर्बिटल्स. एंड लीविंग बिहाइंड a नेट नेगेटिव चार्ज. उसकी वजह से एक नेट नेगेटिव चार्ज आ गया एंड नेट नेगेटिव चार्ज लेफ्ट बिहाइंड इन दिस. ओके. तो उसी का मतलब है कि इफ होल्स गॉट फ्रॉम दिस रीजन टू दिस रीजन, it will leave behind some negative charge here because it will become now more negatively charged on this region. Negative charge here. That is the same thing that electrons यहाँ आ गए इस region में. And electrons, when they came to this region, they increased the potential energy at this region, and that's why there's a bending like this at this particular region. So इसीलिए band diagram ऐसे बन गई, because electrons came here and electron की potential energy यहाँ पे increase हो गई, and this particular thing dropped here because of the kind of holes went here, electrons go here, electron की potential energy increase हो गई. That's the concept of this question. Now, final question is has been asked in GATE 2018. It says that a junction is made between P minus silicon and P silicon. P minus silicon is, let's say, it's the same question, homotype junction. यहाँ पे doping 10 to the power 17 per centimeter cube है, यहाँ पे 10 to the power 15 per centimeter cube है. And you need to compute the magnitude of the built-in potential across the junction. And for it, you're going to use the same built-in potential voltage. KT by Q, ln of concentration on the second side divided by concentration on the other side. And when you solve it, you get you have to take the kT. This is the actual formula for the built-in potential. That's what comes from the derivation. You don't have to use Na Nd divided by Ni square. This basically comes from here when you take the corresponding quantities. But the actual thing is that it is ln of concentration on the one side, second side divided by concentration on the other side, electron concentration. If you write it in terms of whole concentration, then you have to write it concentration of 1 divided by concentration of 2. That is P1 by P2. Here it is N2 by N1. So let's think about this. This is kT by Q ln of 10 to the power 17 divided by 10 to the power 15. This thing is given 26 millivolt. This is ln of 100. This is 26 into 10 to the power minus 3. Ln of 100 is 2.31 into 2 into 1, because you can write ln of 10 to the power 2 as 2 ln of 10. This is 2 into 1 into 2.31. That is the same thing I have written here. I hope you guys know about this. So you solve this thing, you get 26 into 2. This is 42 into 2.31. How much is this approximately? Let's multiply 42 into 2 kitna hua? 2 to the 4, 2 4 is 8, 84. So 84 into 10 to the power minus 3, that means 0.008. That means 0.08. So this is the answer of this question. I hope that is the answer of this question. Is it the answer of this question? Have you solved it? Yeah, that should be the answer of this question. Okay, so I think that's it. Okay, so we are done technically with this session, and we have solved all of the problems in this particular assignment section. A little bit about the junctions. This is the important part. I will continuously highlight it because it requires some sort of calculation at least. And developing these band diagrams is very essential. How you go from a charge profile, how you go from a charge profile to a, this is a space charge region, to a region where you make the rho of x, which is the charge density, q times nd minus q times na. Then how you go to the electric field profile. This is minus xp, this is xn, this is e of x, this is x, this is x, this direction is x. Okay, then how you go from this to this is integrating rho of x, epsilon dx. Let's say from x1 to x2. Then you go from this to this, you obtain electric field as a function of x. And if you want to go to the next step, if you kind of integrate this thing now, electric field, which is not shown in the question, you will get the potential energy profile. You will get, if you integrate this thing now, integral E dot dx, which is the potential but negative. Okay, because electric field is minus dou v by dou x. So you will get the integral of this thing. You will get a potential only.
Okay.
You convert the potential into potential energy, because potential energy is equivalent to electric charge minus times electric charge times the potential. This is the actual band diagram you get. Okay, So you get something like this here. That is the actual kind of band diagram you get from the electric field, basically electric field profile. And from again the electric field profile, so from the potential profile, the potential energy profile, you can get the concentrations n, p as function of x. That means n of x, p of x. मतलब n of x और p of x स्पेस में कैसे वैरी कर रहे हैं ये इससे मिल सकता है. That is the higher part of it. Whatever you get those
Okay. Okay,
curves,
sir.
the variation. You have any question? Why is it lagging?
No, sir. Okay, sir.
Okay, so what you do is that you get, if you know the, let's say, you know the Poisson equation is, you can write it, the Poisson equation is actually like this. Okay, so that is what you write as dou by dou x, dou v by dou x times rho by epsilon. And this particular thing is electric field. That is what you get, this thing. But if you start from this thing, minus dou square v by dou x square equals to rho by epsilon, and you write dou square v by dou x square equals to minus rho by epsilon, you will write rho as q times nd by epsilon. If these things, because these things are exponentially varying with voltage you apply to the device,
Okay, sir.
because this is a potential, you are applying some potential. This is the same thing. You are applying the potential, you are varying the concentrations, and how these concentrations are varying, it is
The
as some
carrier, sir, resist.
ex, exponential of e to the power some exponential of some ec minus ev divided by kt type. And you can write it as minus q some factor e to the power ec minus ev divided by, not exactly like this, you get basically EFN minus EFP divided by KT, which is the difference in quasi-Fermi levels, which is basically the applied voltage, which is basically this V. So you can write this thing as minus Q e to the power EFN minus EFP divided by KT divided by epsilon. And this thing gives you minus Q epsilon exponential of, you can convert energy into voltage as Q times V applied divided by KT. Now you get this equation minus d square V by dx square, यहाँ से यहाँ आ गया, equals to minus Q by epsilon e to the power QV by KT. And this particular equation is solved numerically in all of the device models. You might hear people actually use this in research in order to model the device, because you can solve this equation because there is a potential on this side, there is a potential on here, this side. You can solve it numerically. You guess some potential, you obtain another potential, and it keeps on going in a loop. And you solve it in a, let's say, on a computer or any, you write a program for it for solving this differential equation. Okay, and it gives you the variation of the potential. Particularly technically, it gives you band diagram by solving this equation. If you kind of, if you kind of, I should say, this thing, if you approximate for small voltage, for smaller voltage of the order of kT, millivolt में अगर होगा, let's say of the order of kT voltage हम apply कर रहे हैं, बिल्कुल छोटी voltage apply कर रहे हैं, small signal जिसको कहते हैं. So you know that e to the power x can be written as 1 plus x divided by 1 factorial plus x squared by 2 factorial, which is the Taylor series expansion. So you can expand Taylor series, expand this exponential around that particular around that voltage. And when you expand it and consider only first two terms of the expansion, you get minus dou square v by dou x square equals to, let's remove this minus q by epsilon. 1 plus, okay, there is a minus sign. Yes, there is a minus sign here. 1 plus, oh god, 1 plus qv by kt, removing the higher order terms. And once you get this particular type of relation, you can basically get a characteristics for a device, how the device is going to work if you apply small voltage, how the bands are bending, what is happening to the band diagram. Because you are applying this potential, it is showing up as this particular thing, and you are kind of following it in a loop. Okay, so that is what you need to solve in order to kind of understand the device electrostatics perfectly. And it's a very it's people work on it all the time. Those who do the device modeling, they work on it, they solve this type of equation. This is the Poisson equation in terms of q and d by epsilon. And this is q by epsilon. I guess it is 1 plus e to the power qv by kt. Oops, not, wow, what's this, e to the power qv by kt. Okay, and you need to solve this particular equation. But it's I don't think it's kind of covered in this course, but maybe you might, this particular thing is taught in something called as semiconductor device fundamentals. Not semiconductor, sorry, semiconductor device modeling course. Semiconductor device modeling course. And this is a very kind of simplistic scenario. Actually, it's d square v by dx square is rho times epsilon. You know that rho is actually q into all of the charges that are present. All of the charges. It includes P, N, ND, NA, all of the charges. That is the actual scenario, actual picture. Okay. Then you have to consider P, number of holes, whole variation. You have to consider N, you have to consider ND, you have to consider NA. That will give you the actual picture of it. Okay. So that particular thing is, when you consider all of these things, you get something like d square v by dx square equals to q by epsilon exponential of qv by kt minus 1. And if you expand it around for a small signal voltage, you Taylor expand it. You can write e to the power qv by kt as 1 plus qv by kt plus qv by kt square divided by 2 factorial plus so on and so forth. If you neglect the higher terms for smaller voltage, because if voltage is small of the order of kt, then Vika square will be still smaller. Okay, so you neglect higher order terms, you consider these terms, and you get q by epsilon 1 plus qv by kt minus 1. This goes. You get q square voltage divided by epsilon kt. You can write it as voltage over epsilon kt divided by q square d square v by dx square. You get this equation. Now you have to solve this equation numerically. You cannot solve this equation or kind of analytically, because it's a differential in v, it's a kind of v here. You have to solve, you have to put some potential, obtain a new potential, and you have to kind of loop it using maybe certain numerical techniques. And this particular thing, if you write it as ld square, where ld square is basically, you write it as ld square, you can write it as ld is equal to under root of epsilon kt divided by q square. This is something called as d by length. D by length. And you can write this equation as d square v by dx square equals to v divided by ld square. Now again, it's a kind of simple, becomes a simplistic equation. Now we have to solve this. What this d by length basically shows you, it shows you the spreading of the charge, which I earlier showed you. That if you have a space charges like this, rho of x, positive, negative, it actually looks something like this. And this spreading, charge spreading, is actually the d by length, which is given by under root epsilon kt by q square. It's the debye length. Okay, debye length has different meaning in different scenarios, but this is the actual how a device is simulated, whether it's a PN junction diode, whether it's a MOSFET, whether it's a BJT. Same equations apply everywhere. If you understood diode perfectly, you are going to understand every electronic, I should say, device, whether it's a very high class FinFET, MOSFET, BJT, high electron mobility transistor, something called as HEMT. There are many. If you understand PN diode, you go on understanding the BJT, you go on understanding something called as HBT, heterojunction bipolar transistor. You can understand high electron mobility transistor. Maybe this requires a little bit knowledge of quantum mechanics, but these you can understand by classical kind of electrostatics, the systems, electrostatics. And if you understand now, then you go from understanding this thing to understand the MOSFET, also the you can understand the MOS, then you can go into understanding the different systems, like let's say the FinFET. These are different transistor systems. So this is the overall scenario in the electronics. But the basic start is from this. You have to kind of entirely understand the electrostatics of the PN junction diode. Then you can kind of jump onto these regions, other parts. Okay, I think that's it for today. So this was the brief introduction of how these equations play a crucial role in modeling the carrier electrostatics inside the device, and that gives you a very, I should say, these equations give you the estimate of how device is going to respond to different voltages in different environments. Let's say if you are applying some high voltage, how the device is going to get affected, what will be its performance in different situations under different conditions. What will happen if we go for if we take the device at a colder temperature. You need to solve these equations numerically or something called as by simulations, and it gives you the idea of how device works in real life situations. Then you go on fabricating this device, and it approximately works like that. That is the beauty of this equation and beauty of this maths. And that's what the, I should say, half of the electronics device engineering is all about. Modeling. It's not the modeling which people do on the ramps. It's not a ramp walk, but it's a device modeling. It's the simulations simulations to understand the behavior of the system in the changing environment. Okay, I think that should be it. I will just stop here, and I'll be stopping exactly at 8. If you guys have any question, then you can ask any question if you have. Thank you.
Sir, I got this solution of the equation in the book, Sir, Modern Physics
Solution
by
of which equation?
uh, of this Poisson equation. So,
This
with,
one.
yes, sir.
You can under certain approximation you can solve it exactly. You can solve it by hand.
Modern Physics by written
Hmm.
by R. Milligan.
अरे this is a differential equation dy by dx square is equal to some a times x. इसको तो सॉल्व कर सकते हो ना,
Yes, sir.
राइट? तो ये तो
Okay.
मतलब ये तो बहुत इजी टास्क है इसको सॉल्व करना. You can solve it. So maybe you might require certain some steps,
Thank
but
you,
this was a
sir,
very,
for your simplification.
sorry.
Thank you for your simplification, sir.
Yeah, I try to simplify the things because I don't like to add jargons, maybe some sophisticated, मतलब वो बड़ी बड़ी terms फेंकना, तो that is not the part of my teaching. I hate using those terms because the only fundamental thing is that the other person should get the concept in a very simpler fashion, not in I can use the terms like I can tell you that this is because of quantum mechanical aspects, quantum mechanics, वो ये, but to the whatever you are taught right now in this course, it does not deal with those jargons. So you have to keep it simple. And thank you for this nice gesture, I should say. And somebody has written a message in the call in call message I can see Sarala. Thank you for this, and it's my pleasure that I'm teaching on this NPTEL for this course, and thanks to Professor Naresh Imani particularly. If you guys have any question, you can ask me any of the questions you want me to discuss. I have 5 more minutes, then I'll be ending this meeting. Okay, then I should stop sharing screen. All right. Okay, then let me just end the meeting if you guys don't have any question. Thank you for this session. See you again on next week. Bye bye.
Bye, sir.
Bye. Okay, let me this.